Yeah, so good afternoon, everybody. This is Roger Frechette. I'm the managing principal of Interface Engineering, and I'd like to welcome you all to our bi-weekly free webinar series on high performance buildings. This is the sixth session that we've held this year. We've got a number more to come before the year is out. And just a real quick note about Interface Engineering. We are a mechanical electrical engineering design firm, if you don't know us. We've been in business for 51 years. We have an office downtown Washington, D.C. We're also located in Portland, Los Angeles, San Francisco, Oakland, Hawaii, Chicago as well. And we have a great presentation lined up for you today. So I wanted to go ahead and introduce our speaker, Mr. Joseph Diano. Joe is an associate principal and senior mechanical engineer with Interface, located in our Washington, D.C. office. Joe has a master's degree in architectural engineering from Penn State University. He is a licensed mechanical engineer. He is also a LEED accredited professional. Joe and I have worked together for many years on a number of significant projects, including several net zero energy projects and several projects that have used the specific technology that Joe is going to be talking about today, and that is radiant systems. So I don't want to take up any more time. I do want to let everybody know that Interface is an AIA accredited provider for these series. The AIA course number for today is M20-0616. However, simply by registering today and providing your email, you will receive a certificate through the email of your attendance with your one learning unit. And also want to say, please do collect your questions. There is a field within this GoToWebinar that allows you to put your questions, and I'm sure Joe is going to answer as many questions as he can at the end of the presentation. So without further ado, Joe, please take it away.
Thank you for the introduction, Roger. I appreciate it, and welcome everyone. As Roger mentioned, this is our sixth installment of Interface Engineering Presents High Performance Building webinar series. And today we're going to be talking about radiant systems for modern buildings. As Roger mentioned, this is an AIA accredited course, and I believe it is one learning unit. So as this is an AIA course, I will go through the course description. I won't read everything on screen here. You can all follow along, but really, the genesis of today's presentation is that, with the sustainability and energy performance goals these days, on an HVAC standpoint, we're looking at a lot of different systems to try to meet some of these efficiency goals. And radiant heating and cooling systems are one type of application that really has a lot of benefits in that area. So today, our learning objectives are to, one, gain an understanding of the fundamentals behind radiant HVAC systems. Two, we're going to learn about the different types of radiant HVAC systems that can be utilized. We'll have a discussion about some of the specific design parameters associated with these types of systems and some of the other application considerations which a designer or engineer should take into account when pursuing a radiant type system for their project. So first, what is radiant? We will get into that and describe what this system is and how it's different than things you may have seen in the past. Types of radiant systems, some of the design parameters, application considerations, and then finally at the end we'll open it up for a question and answer section. So let's dive right in. So what is radiant? Well, the first thing I'd like to go through is kind of the history of radiant. It seems with any interesting technology and any good idea that we've had, somebody else had that idea 12,000 years ago. So you can trace the origins of these types of systems back to the 11th century BC in China. The word Kong, which ultimately would become known as heated bed, started to appear. And then as far back as 5000 BC in China and South Korea, there's archaeological evidence of these types of systems that are known as the Kong, Daikong, or Ondal systems. And here you can see on the left kind of what these systems were and how they started. It really started with the fact that, you know, every home was going to have some sort of cooking stove, and so there was a source of combustion and heat already available. So as far back as 5,000 years ago, they were already taking the waste heat, the byproducts from this combustion, and channeling it in order to not only cook their food, but to heat their homes. So the image in the center shows a traditional Ondal system, which has, you know, the cooking stove, and then the byproducts of that cooking stove are actually sort of ducted underneath a raised platform. And that raised platform then heats up. The material itself heats up, and that in itself is radiant heat transfer. So this is kind of the first examples of radiant floors. The image on the left is a partial reconstruction of a site dated around 3000 BC that shows how some of these Ondal systems were built. They have pillars that hold up the floor structure, and that void space below the floor structure is where the energy is then transferred through the space. Around 500 BC in Greece and in the Roman Empire, they started to adapt some of these technologies that were seen in Asia. And as was typical for the day in ancient Rome, they really would take an idea and expand upon it, sort of on orders of magnitude and orders of scale. And so what you're seeing in the image on the right is what the Romans referred to as a hypocaust system. And this is kind of like the systems we were looking to use in Asia, but on steroids. They would have much bigger systems which were able to create radiant surfaces in much larger areas. The image on the right here is actually of an ancient Roman bath. So they would use the technology to heat the water in the Roman baths. So by 50 BC in China, Korea, and in the Roman Empire, these types of systems were being used and were very common. In Rome, they started adapting these and doing different things with these types of systems. So it wouldn't only be the raised floor platforms, but they started integrating the flues into the walls. And what that allowed them to do was heat up the wall surfaces as well. So now you had radiant surfaces that were not just the floor, but were also the walls as well. Around 500 AD, the use of these types of systems continued throughout Asia, but in Europe, they actually saw sort of a reversal. These systems kind of fell away, were not as popular, and essentially were replaced by open fires and rudimentary forms of fireplaces. But by 1000 AD, in Asia, they were still moving forward with these types of radiant systems. They were making them larger, where it used to just be an Ondal system would heat a small platform. They were then adapting them to heat essentially the entire home. So the scale started to build up and up over time. Moving forward into more recent times, in 1600 in France, these radiant systems started to sort of pop up again. And they were greenhouses in France designed using heated flues in floors and walls. So very similar to the technology that was developed thousands of years earlier started to arrive again. In 1700, Benjamin Franklin was studying ancient Asian and French culture and noticed that these systems were being used, and out of that came the invention of the Franklin stove. Moving forward to 1894 in Germany, the Reichstag building was built. And at the time that this building was built, it was essentially considered to be a technological marvel. There were technologies applied in this building that really hadn't been seen on this scale to date. And the building itself actually utilized thermal mass for radiant heating and cooling. In the United States, we were a little further behind the rest of the world in terms of adopting radiant technologies. One of the first that started to look into this and think that it was something that could make a lot of sense was Frank Lloyd Wright. In 1905, he traveled to Japan for the first time, and he was struck by some of the technologies that he had seen used in Japan and throughout Asia for home heating systems. In 1907, in England and in Europe, there were various panel warming systems that started to become patented. And these systems were using small pipes that were run in sort of floor or wall panel systems, and really were the precursor to some of today's radiant technology. One of my favorite anecdotes is the one from 1933 in England. So it was somewhat by chance that a material that is so commonly used today in radiant systems was discovered. And it happened when there was an explosion in a chemical laboratory that was experimenting with ethylene. And the explosion created this wax-like substance. Well, that wax-like substance would become polyethylene. And from polyethylene, that is where we get today's PEX piping. In 1937, Frank Lloyd Wright designed one of the first, or considered possibly the first, Usonian home in the Herbert Jacobs house. And he integrated what he had learned in Japan into the radiant floor systems for these Usonian homes. Moving into 1930 to 1950 in Europe, beyond radiant heating, they started experimenting with and applying technologies to do cooling as well. They realized that these systems were great for heating, but they could also be utilized in cooling. And the 70s and 80s in Korea, they started to move on from the traditional ondol type, which was using open combustion, and they started using hot water. And this was primarily because in the 70s and 80s, there was a building boom, and they started building taller and multi-story, multi-floor apartment buildings and residential buildings. It was very dangerous to use these open fire type systems. So they started to transition to hydronic systems, which actually look very much like what we are utilizing today. By 1985 in Europe, floor heating in most of the temperate climate regions was commonplace in residential buildings, and was starting to find its way into non-residential buildings as well. And that moves us to today, where we're seeing radiant systems being applied all throughout the world. They are very popular in portions of Asia. They are very popular in Europe, but they're also gaining popularity in other areas, including in the United States, because the technology and the quality of our buildings is allowing, climate regions that used to shy away from radiant systems to really start to adapt this technology. So how does radiant work? So this is a very scientific looking slide about the three types of heat transfer. And if we all go back and remember our physics lessons and our heat transfer classes in college, the three forms are conduction, convection, and radiation. So if you're like me and you're more of a visual guy and don't really like these types of visuals, I have another one that I think makes a lot more sense. And it's essentially boiling a pot of water, because you have all three methods of heat transfer involved in that. You have the radiation from a fire, so that is being transmitted in the forms of rays or waves or particles to the pot of water itself. Then you have the water inside of the pot that is being heated through the process of convection. And as I do probably monthly when I'm cooking, I forget to use a pot holder, and I'll grab the hot handle of a pot, and I will experience conduction when that heat is then transferring from the handle of that pot into my hand via direct contact. So how is radiant heat transfer different? Well, radiant heat transfer is through electromagnetic waves traveling through space, which honestly is probably the coolest sounding mode of three modes of heat transfer, and is why I like it so much. A simple example of radiation is sunlight. Sunlight is essentially light that is traveling through the vacuum of space, a shortwave radiation, and warming the Earth's surface. In radiant cooling, electromagnetic waves from the occupant are being drawn toward the cooled surface, which results in the occupant experiencing a cooling effect. And this is sort of, back to physics 101 classes, where energy travels from a high state to a lower state. It's not the radiant panel projecting cooling onto you. It's you rejecting your heat to the radiant panel, which actually creates the sense of cooling. So how is this different than perhaps our traditional all-air systems that we find in a lot of our buildings today? So forced air heating or forced air cooling is really relying on the process of convection to heat and cool the space. You're taking a volume of air that has either been cooled or heated, and you're introducing that into the space. And then the mixing by convection in the space creates what hopefully is a suitable air temperature for occupant comfort. Now, there are some issues with these systems, and they can be resolved in a lot of different ways, but some things that are common are the idea that when you're using overhead heat or overhead air for heating, you could have cold feet and a hot head. There's a lot of thermal stratification there. Radiant is a little bit different in that it's not relying on convection. It's not relying as much on air temperature in the space, and it's really relying on that direct radiant energy transfer from the occupant to the radiant surface. So now we're going to get into the types of radiant systems, and I'll preface this with saying there are so many different types. I tried to distill this down to the ones that I think are the most common and that they're seeing today, but there are a lot of options out there. And really, if you're ever interested in these things, you can do a 3-hour presentation just on the types of radiant systems. So the first one I'd like to talk about are radiant floors, and specifically concrete slab radiant floors. These are typically found to be, slab on grade or slab on below grade, or potentially a slab on slab application. And that's the most common method that you're going to see for commercial radiant floor concrete slabs. And essentially, the way that these work is the PEX tubing is poured directly into the slab. There's a lot that goes into the construction to make this work. You'll notice in both of these images that it's showing a layer of insulation below the PEX tubing. And this is extremely important because energy is going to want to radiate in every direction. And so by putting the insulation in, you're helping direct the energy that's being transferred from the PEX tubing into the slab upwards and into the space where it can actually exchange with the occupants in the space. So one point to make is that the PEX-A tubing, it does not compromise the structural integrity of the construction. There are a lot of different ways that you can apply this. There are probably dozens and dozens of slab details showing how that these can be applied. It can be put directly into a structural slab. It can be put directly into an overpour or a topping slab. So there's several different ways that it can be done. And the other thing to note about radiant floor slabs is this is considered to be a high mass radiant system. And a little further on into the presentation, we'll talk about the difference between high mass and low mass radiant systems and the pros and cons of each. So here you see an image of a very large, very open space that is utilizing a concrete slab. Now, this is the system before it has been poured, and I really like these images because it shows a lot of how these systems are installed, how they're laid out, and how they're zoned. You can see by the sort of geometric patterns that on the ground that each one of these areas is a separate circuit, right? So each of these circuits then get routed back to what we call a radiant manifold. We'll talk a little bit more about that in a second, but the takeaway from this image is that you can really cover extremely large surface areas with radiant floor systems, and oftentimes it's required to cover a very large area in order to get the capacity you need to heat and cool the space. So here's a couple examples of radiant floor slabs actually being poured, and to be quite honest, it's not that dissimilar from simply pouring a normal concrete slab. Care must be taken that the tubing is appropriately protected and secured into place, and then the concrete is poured on top. And in both images, you can see the layer of insulation below the radiant tubing. Another type of radiant floor is a wood subfloor system. Now, it's not too dissimilar from the concrete system in that you're running PEX tubing beneath some sort of substrate to transfer energy into the space. However, this would be considered a low mass radiant system because you're not getting the benefit of the thermal mass of that concrete. So the system traditionally is put into what I would call like a wood subfloor track. So the bottom right image shows the radiant tubing installed in preformed channels in a wood subfloor. And then there are aluminum panels that are connected to the tubing. And really that's just to increase the heat transfer from the tubing to the floor system. Oftentimes you will find these types of applications in predominantly wood construction, or also in retrofit applications where pouring a new concrete slab simply isn't possible. So either of the two radiant floor systems are going to likely utilize what we call circuit manifolds. And these manifolds are very important because this is where all of the PEX tubing that gets run into floor comes back to. And really you want to have these manifolds located as close as you can to the actual zones themselves. And so to allow for that, the industry has essentially developed manifold systems that can fit into a normal stud wall. So it gives a lot of benefits in terms of flexibility of where these types of manifolds can go, and it helps reduce the length of these circuits. So the next type of radiant system I'd like to talk about are radiant ceilings. And here I've shown 6 examples, but I could probably put together 60. There are a wide variety of options of radiant ceiling panels that essentially can suit almost any architectural aesthetic. So in the industry and in these systems as they're applied, predominantly you're going to see aluminum or steel radiant panels. And these aluminum and steel panels are what we would consider to be a low mass radiant system. And again, they can be integrated into ACT, acoustic ceiling tile ceilings, into drywall, into metal ceilings, or the radiant panels could actually become the ceilings themselves. So the first type of radiant ceiling panel I'd like to talk about is what is known as a modular panel. And I also consider the modular panel to be sort of a tray type application. They're going to come in standard sizes, whether that's 2x2, 2x4, 2x6, 8, 10, etc. And the modular panel is really meant to fit in a normal ceiling grid. And the way that they work is they have copper tubing run on top of the panel, and that copper tubing is then connected directly to the aluminum or steel panel via heat sinks and what is known as thermal paste. So the heat sinks and the thermal paste are very important because it enhances the energy transfer from the fluid running in the copper tubing to the panel itself. Now, there are a lot of different finish options. You can have the traditional smooth face finish. You can have a perforated face finish. A lot of times the perforated face is utilized where there are acoustic concerns. And so you will use the perforated face and have an acoustic backing on the panel to try to absorb some of that sound. The face finishes can be made to match acoustic ceiling tiles. They can sort of silk screen on top of these panels to make them blend in. So there's a lot of different options when you're looking at modular panel types. And here you can see an example of a modular type application. In this case, they are utilizing the perforated face panels, and they're using the panels themselves to make up the ceiling. Otherwise, there would be no ceiling in the space. So it creates a unique architectural aesthetic, and it also sort of showcases the HVAC system for the space. Another type of radiant ceiling panel is what we call linear panels. Now, these are very similar to the modular type. The real difference being that it's just an extruded aluminum or steel shape, and the idea is that they are very linear. You can have very long runs of these seamlessly connected together for a very clean look. The way that the energy transfer works for the linear panel is almost identical to how the modular panel works. You have the copper tubing essentially attached to the backside of the aluminum panel itself. Again, there are a number of different sort of surface varieties that you can select from, many different types of perforations, smooth panels. You can also have castellated panels, which create a very unique aesthetic in the space when they are used. So there's a lot of different options architecturally when you're looking at these types of systems. And here you can see an example of a linear panel system that has been integrated into a traditional 2x4 ACT ceiling. And you can see that it creates a very consistent look all the way across the linear panel. Again, they're using the perforated type here, but you could easily see, a smooth panel used here as well. And the other unique thing is that with radiant systems, not every panel that gets installed into the ceiling necessarily has to be active. Sometimes architecturally, you may want a look of a very clean linear length, but you don't actually need all of those panels. So the companies offer their panels essentially without the copper tubing attached to the back so that it creates the same appearance but isn't necessarily an active portion. Another type of radiant ceiling panel is what is known as a radiant sail, or oftentimes they are referred to as chilled sails, but they can also do heating as well. And the primary benefit of a system like this is that the increase in surface area of the panel itself, because it is using arched or rounded panels, allows for a greater capacity per square foot of ceiling space. So sometimes when you need a little bit more capacity than perhaps a modular or linear panel can give you, a radiant sail can be a good option. It also creates a very unique architectural look to use the sail. It kind of breaks up the flatness of a normal ceiling plane and creates some architectural interest, I would say. At least I think it's interesting. Here you can see an example where chilled sails are used over the occupied portion of an open office floor plan, and the remainder of ceiling is kind of a wire mesh or metal mesh ceiling construction. So another type of radiant ceiling is the overall metal ceiling. And there are companies out there, Armstrong comes to mind because they've been very big in the metal ceiling industry for a very long time. And these types of metal ceiling systems really lend themselves well to radiant because you already have the metal surface available to you. It's really just activating a portion of that surface in a similar way to the modular and the linear panels, where you simply run copper tubing and you're attaching that directly to a portion of the metal sealing system. Now, these metal sealings are not 100% active radiant sealings. It may be portions of the sealing system are active and portions are inactive, but the real benefit of the metal sealing system is that it creates a very homogeneous sealing look. You can't tell what portion is active and what portion is inactive. It all sort of looks the same and has a very, very clean look in that regard. Another type of radiant sealing panel is a drywall panel. So sometimes you have drywall ceilings, whether that is in a conference room, an elevator lobby, just areas that don't want to have an acoustic ceiling tile ceiling. But if you're utilizing a radiant system, you need something that works well in that type of environment. And these drywall radiant sealing panels can do exactly that. And they come prefabricated from the manufacturer, essentially with all of the radiant tubing already installed and with drywall finished on the face of that panel at the factory. So essentially all you have to do with this type of system is bring it out into the field and install it into your ceiling adjacent to a normal drywall ceiling panel, and then you mud the joints, you tape it, you sand it down, and then you paint it as if it was any other surface. And essentially what you end up with is a completely seamless drywall ceiling with portions of it activated as radiant cooling and heating. It's also a unique product in that it comes in a 4x8 sheet and can essentially be field cut into different dimensions, whether that's split in half vertically or horizontally to give you a 2x8 or a 4x4 type application, or it can be quartered into a more traditional 2x4 panel size. So it offers a lot of flexibility in terms of how you order the product, how it can be installed, and how it's treated in the field. So there are a few other unique radiant sealing options that I wanted to touch on. These are things you don't see as often, but I include them here because, should the opportunity arise to use this, it's just good to know that there are so many different types of applications for these types of radiant systems. In the upper left, you see essentially a light shelf that's been installed as part of a double height atrium space. And so this light shelf then doubles as a radiant surface. And that radiant surface can be very useful in counteracting some of the energy transfer through that glass wall system. And so this can be integrated into a light shelf system if that's being designed. In the bottom left, we see a radiant sail application, but this radiant sail is unique in that it actually has an acoustic fabric over it. And this acoustic fabric has been designed specifically to maintain the capacity of the radiant panel and the efficiency of its heat transfer. So anytime you put a piece of fabric or anything on top of a radiant panel, you're kind of adding an insulative layer and decreasing the performance. So some of the technology these days have been looking at how do they create these fabrics that allow maximum heat transfer, but also provide a maximum acoustical benefit. And in the bottom right corner, there's a type of modular panel that is a little bit different in that the copper tubing is not attached in the same way that you would find with a lot of modern radiant panel designs. The copper tubing is actually set in graphite, and the graphite is then thermally bonded to the steel panel. And what this does is really try to increase the effectiveness of the heat transfer from the copper tubing to the radiant panel. And the ultimate benefit there is that these panels can be a slightly higher capacity than a traditional aluminum radiant sealing panel. So we talked about floors and we talked about ceilings, and that only leaves one surface left, which are walls. And as you may have guessed, a wall can be radiant too. So any surface in any space can be made to be radiant. We don't see these applications as much in a commercial building. Oftentimes they're sort of very specialized in residential construction, but that's not to say that they couldn't have an application in a commercial building. So I really just include this as an example to know that, should the need arise where a radiant wall might solve a problem in terms of thermal comfort in your building, it is a possibility. And you may notice that these systems look very much like the wood subfloor systems, because they are almost identical. It's essentially a wood subfloor system turned into the vertical and placed on a wall. And when you construct them, very similar to the drywall systems that we were looking at, you simply drywall right over these systems. So the drywall will reduce the capacity a bit, but in a certain situation, you may be able to still get sufficient capacity from the wall. So I'd like to dive into a little bit of the design parameters for radiant systems. And again, I tried to keep it high level. We could do a 4-hour or even an all-day presentation on the very specific design requirements for radiant systems. But I tried to keep it high level so that you can get the main ideas of what we're trying to accomplish. But it should be noted that these types of systems do require a little bit more design than maybe an all-air system might. And so it's just something to keep in mind whenever you're moving forward with a radiant system, that there are a lot of calculations and things that need to be looked at to make sure that they're effective. So let's answer the question of why radiant? Why would I want to do this? Well, we already mentioned the idea of energy efficiency and how these types of systems can improve efficiency in a building. So it can improve the overall HVAC efficiency, but it can also specifically improve the efficiency of your cooling and heating plant. And the reason is that radiant systems are using what is called elevated temperature chilled water and low temperature hot water. So that's kind of a contradiction when we're talking about hot chilled water and cold hot water. But the idea is that the warmer the chilled water temperature is, the less energy it takes to produce that chilled water. And the converse is true on the hot water side. So the lower temperature hot water we're making, the higher efficiency our boiler is going to have. So even a very high efficiency boiler creating, say, 120-degree water, that's going to be around 88, 90% efficiency. But if you can take that down to 80 degrees, 90 degrees, now you're over 94%, 95, 96%. You're very efficient on your systems there. So that really does a lot to add to the energy efficiency of the building. Another primary reason that radiant is great, and this is one of my favorite images, and I always talk about this when I'm having any discussion with an architect or an engineer who's interested in the technology, the lower transport energy usage has a huge benefit for radiant systems. You can see in the image here, we have a 1-inch diameter pipe and a 16 by 16 air duct. Well, due to the density and heat transfer capacity of water versus air, those two objects can transfer the same amount of energy. So when you're talking about very small pipes and pumping fluid versus very big ducts and pushing air around, I mean, you can find 50 to 75% reductions in fan horsepower when you're using a radiant system over an all-air VAV type system. And all in, when you're looking at both fan and pump energy, savings on the order of magnitude of 30 to 40% are possible. So the other major benefit of a 1-inch pipe versus a 16 by 16 duct is reduced space requirements. And this is something that, architects that I've worked with that, have wanted to adapt this technology. This is one of the prime movers sometimes, is that they're trying to reduce the amount of space in the plenum that the HVAC system takes up so that they can either reduce the floor-to-floor height for each floor of the building, or to maximize their ceiling heights, or both. So you can see here the image on the left shows what would be more of a traditional all-air VAV type system, where you have larger ducts, distribution from VAV boxes to diffusers, and it takes up a decent amount of space. The image on the right shows much smaller radiant systems. These radiant systems tend to be very thin. You have small size piping that is running above the ceiling, and any ventilation ductwork that is there is just for that. It's for ventilation only, if not for heating and cooling. So the sizes are much smaller. And you can see, up to 12-inch reductions in plenum depth when you utilize these types of radiant systems. And, everybody knows that in DC, we have very tight floor-to-floor heights due to the height of our buildings and the restriction of the height of the buildings. So radiant systems can allow the opportunity to have, much better ceiling heights than you might otherwise have. Another reason why radiant is a great choice is improved occupant comfort. ASHRAE Standard 55, which is the thermal environmental conditions for human comfort, has 6 factors that it lists that affect human comfort. One is air temperature, then there's also radiant temperature, humidity, air velocity, clothing, and metabolism. So forced air systems are trying to maintain comfort, but they're not addressing necessarily every aspect of human thermal comfort. They leave out the radiant component to some extent. And so radiant systems try to address that by adding that radiant component of thermal comfort back into the equation. Now, the image in the center is really showing kind of the sweet spot for operative temperature, airspeed in a space. The point to make here is that operative temperature is not the same thing as air temperature. And that's very important in radiant systems because operative temperature is essentially the combination of what is known as mean radiant temperature and air temperature. And I won't get into too much of the science behind the image on the right, but I included it just to make the point that when you do the calculation and you start to take into account the various surface temperatures in a room and the air temperatures within a space, you can find that a space that has an air temperature of 78 degrees actually has an operative temperature of closer to 76.7. And what that means is that someone can be comfortable in a space where the thermostat has been pushed up to 78 degrees. And anytime we can raise the thermostat temperature, we're going to find that that's going to improve the efficiency of our buildings. Now, to the discussion of high mass versus low mass radiant systems, really it's all about energy retention. And what I mean by energy retention is a low mass system does not really have the ability to retain its energy for a very long period of time. It essentially needs to be on and active in order to be doing its radiant heat transfer to occupants in the space. As soon as you shut the system off, in a very short period of time, that system will then essentially become the same temperature as the environment around it. High mass systems are very much different in that they can absorb a very large amount of energy. Thinking of a radiant floor system that has been placed into a concrete slab. That concrete slab can absorb this energy as well as transfer that energy back to the space over a very long period of time. Low mass systems for cooling and heating capacities usually are higher than a high mass system, but the low mass system is able to respond very quickly to changes in the thermal environment. And that becomes very important when you're trying to think about what radiant system might be right for this space. If we're talking about small conference rooms and closed office spaces, typically a low mass system is going to be a better option because it's able to react very quickly. If someone hasn't been in their office all day and then goes in and thinks it's hot and they lower the thermostat, a low mass system is going to be able to react quickly to that. A high mass system may not. Another aspect that's unique to radiant design is what is known as radiant asymmetry. And this is really how people react to surface temperatures that are around them. And this isn't something that maybe we look at enough, and on all air systems, we hardly look at it at all because we're less concerned with the temperatures of these various surfaces. But when we're doing a radiant system, you really have to be concerned about, walls, ceilings, floors. Are they warm? Are they cold? Because if they're too warm or too cold, that's going to have a very negative impact on occupant comfort. And there are design parameters that show you kind of what the temperature delta can be for these various surfaces before someone is going to think that they're uncomfortable. And we'll get a little bit more into that here in a minute in terms of what these surface temperatures really want to be for various radiant system types. So if we look specifically at radiant floor design, and in this case, radiant floor slab design, I have a table here that shows capacity, surface temperature, supply water temperature, and the water temperature delta T, which is essentially the difference between the supply and the return temperature. And these are four of the very important factors that need to be taken into consideration when you're looking at these radiant systems. There's many more beyond this, but I think for a high-level discussion of understanding how these work, that these four are maybe the most important. So when you look at the capacity, on the cooling side for a radiant floor slab, having a typical capacity of 12 to 15 BTUs per hour per square foot is quite low in comparison to all air systems. And it's important to recognize that the capacity is lower because we'll discuss a little bit further later on kind of how keeping the loads down in your building will allow for the application of some of these radiant systems. The good thing with radiant floor slabs is that when they're in contact with direct solar radiation, whether that's a lobby that has double height glass or an atrium space, the capacity can jump way up by a factor of 2 on the cooling side. And that's really because it's absorbing this energy into the slab before it's getting re-radiated back into the space. On the heating side, there's a bigger, I would say, band of heating capacity possible with the floor. Anywhere between 15 and 40 BTUs per hour per square foot can be achievable. And a lot of that is going to depend on the surface temperature and what supply water temperature you're using. And that's a good segue to talking about surface temperature. So because people are going to be in direct contact with the radiant system when you're using a floor slab, the surface temperature and maintaining the appropriate surface temperature is very, very critical. In cooling, you really don't ever want to take that temperature below 65 degrees. Anything below 65 degrees, people are going to start to have, literal cold feet, and they're going to start to experience this radiant temperature asymmetry, and they're going to be uncomfortable. And the same is true on the maximum end for heating. So 84 degrees is about the highest you would want to go with a radiant floor slab before, again, people's feet are going to be warm and they're going to be uncomfortable. Typical supply water temperatures for radiant floor slabs between 55 and 58 degrees. And again, that's quite a bit higher than you would see in a traditional all-air system, which might use anywhere between 40 to 44 degree chilled water. On the heating side, again, a little wider band of temperatures that are possible, but usually between 90 and 120 degrees. We find that around maybe 110 or 115 seems to be the sweet spot between energy efficiency and maintaining that maximum temperature. And you're also looking at smaller water temperature delta T's for a radiant floor slab system. A normal cooling coil might have a chilled water delta T between 10 to 14, sometimes up to 16 degrees. For these radiant systems, you're getting a smaller delta T, usually between 5 and 8 degrees. On the heating side, you're looking at somewhere between 5 and 10 degrees. So the important thing when we're talking about these water temperatures is, again, you want to be able to use the highest chilled water temperature that you can and the lowest possible hot water temperature that you can to meet the space loads, the space sensible loads. That's the ideal scenario. Another important aspect of radiant floor design is the aspect of zoning. So all of these systems need to be zoned out appropriately so that you're addressing both the interior loads, exterior loads, you're keeping the circuits close to where the radiant manifolds are located, and that you're maintaining comfort conditions throughout a space. In very large areas, you're going to have, 4, 6, 8, 12 different circuits serving that zone. So each of these circuits needs to be laid out in such a way that you're able to maintain a consistent thermal environment. And it's also important when you're talking about zoning because it goes back to the idea of the manifolds that you're using for these radiant floor systems. And their locations can be very critical. Wouldn't be the first time that I laid out a radiant system and thought that I had a real good idea of where I wanted my manifold to go, only to find out later that that's an architectural feature wall and they don't want to see an access panel, etc. So it's very important to work, the design team work together to figure out the locations for these. And then there are so many different possibilities when you talk about the circuiting arrangements. Working directly with the radiant tubing manufacturers is a great way to utilize their proprietary software that can assist the designer in laying out some of these spaces. You can give them your loads, surface temperatures that you're looking for, building constructions, and they can work with you to help develop these circuiting layouts. And finally, one thing that's very important to talk about when we talk about radiant floor design is floor coverings. In an ideal scenario, we're not providing any floor coverings at all because anything that we put on top of this radiant slab is going to be an insulator and it's going to reduce the capacity of that slab. Now, the reduction in capacity varies depending on what it is that you're looking at. So if you're looking at maybe a thin, dense stone, it's not going to have that much of an impact on capacity. But when you start to look into wood flooring and you start to look into even carpet, now you're really reducing the capacity of the system, and you need to evaluate whether a radiant floor is going to be the right application. It's also very, very important to find out what the sensitivity, and this is maybe most true for wood flooring applications, because some wood floors can be very sensitive to not only minimum and maximum temperatures, but the range between those two. So oftentimes when we have applications for radiant floors that want to have a wood surface, bamboo comes to mind, because bamboo is a very structurally consistent wood that does not expand and contract as much. Now let's move on to radiant ceiling design and look at some of the design parameters for these types of systems. You can see here that from a cooling and heating capacity standpoint, that we've definitely bumped up a little bit from what we were looking at with the radiant floor system. So a typical radiant cooling panel system is going to give you anywhere between 22 and 33 BTUs per hour per square foot. The 22 would be on the low end, and that would be more indicative of like a drywall panel application. And having a high end of around 38 BTUs per hour per square foot at a perimeter is kind of the max that you're going to be able to get, and that would be with a steel radiant panel that has the embedded tubing. So there are a bunch of options there, and there is a bit of a range, and it's very critical that you understand what the loads are in your space to make sure that you're making the right selection. You can see that the surface temperature minimums and maximums are a little bit different than we were looking at with the floors, and it makes sense because if you have more capacity, you probably have a higher temperature surface. So for most cooling applications, we want to limit that temperature to around 60 degrees at the surface, and in heating around 100 degrees. Sometimes if you have a very low ceiling, that heating number may need to come down. So you really have to analyze sort of all of the physical aspects of the space to figure out what are my ideal temperatures going to be. The good thing is that for a radiant ceiling panel system, you're essentially using the same elevated chilled water and low hot water temperatures that you're using with the floor system, which is kind of nice because you shouldn't view these systems as something that has to be all or nothing. It has to be all radiant floor or it has to be all radiant ceiling. You can actually combine the two in various portions of buildings where they work the best. There is a maximum limit, though, of how much of the ceiling you want to be sort of active radiant ceiling panel, and that limit is around 70%. Truly, we'd like to design closer to maybe 40 or 50%, but that may not always be possible depending on the load in space. So here you see another important example that comes into play when we're talking about radiant ceilings, and that's the concept of coordination. When you're taking 50 to 70% of the ceiling and making it active radiant ceiling panel, that doesn't leave a whole lot of space left for, lights, fire protection, fire alarm, AV/IT equipment. All these things need to be coordinated. So the image on the left is a mechanical drawing. The image on the right is an architect's RCP. And the end result of that is this space. So this is the actual space that those two drawings were showing. And you can see there are quite a number of things that need to be integrated into that ceiling. So over the conference room table, you have AV/IT speakers, you have fire alarm devices, lights, and then adjacent to that area on either side over the seating area, you have the metal radiant ceiling panels. So there's a lot of coordination that goes into making these systems work. Another important aspect of radiant ceilings is access. If you're going to cover so much of the ceiling with these radiant panels, you need to be able to get above it. So it's very important when you're designing these that you have access in mind. Most radiant ceiling panels can have sort of a hinged access system where you're able to kind of fold down the panel. And this can be done without turning the system off, without draining anything down. And that's done with these, you can see the silver flexible connections to each radiant panel. Those flexible connections allow it to be opened and closed without breaking these connections. So application considerations. I want to touch on a few things that are very important to the design of these systems that may not have to pertain to the system themselves. Probably the most important is your ventilation, air, and dew point control system. More often than not, when we are looking at radiant panel applications or even radiant floor applications, we are going to couple that with a dedicated outside air or DOAS system. And the DOAS system is going to handle 100% of the latent load. And it's important to remember for these types of radiant systems that the radiant system is only going to handle the space sensible loads. It is not doing any latent cooling whatsoever. If it is doing latent cooling, that means it's going to have condensation on it, and that's a very bad thing. So that's why the tight space dew point control from the DOAS system is so critical, because we want to avoid having condensation. And what that means is the DOAS system is going to maintain a dew point temperature in the space that's 2 to 3 degrees below the surface temperature of the radiant system to make sure that there is no condensation. Another thing to note is that when we're talking about the ventilation air or the supply air to the space, that radiant systems work very, very well with displacement ventilation systems. So a radiant ceiling in combination with underfloor air or a displacement ventilation system or a radiant slab with wall-mounted displacement ventilation works very well. So it's something to keep in mind when you're thinking about the air side design for a radiant system. Another thing I wanted to mention is the chilled water and hot water design temperatures. We mentioned that we're using elevated temperature chilled water and low temperature hot water. Well, on the hot water side, that may not be too big of an issue. Typically in today's modern systems, you can use low temperature hot water at both the air handling unit and your sensible cooling device and radiant panel or radiant floor, and without much of a problem. But on the chilled water side, because we have to maintain that dehumidification, 55 to 58 degree water is not going to be cold enough to essentially do the dehumidification that you need to do. So depending on the size and the complexity of your chilled water plant, there are a lot of different options. Sometimes on a very small plant, you'll simply put in a heat exchanger like is shown in the image on the right and create a separate elevated temperature chilled water loop for your radiant system. But on bigger systems that have multiple chillers, there are other very unique and interesting options that can maximize the efficiency of that plant while simultaneously creating the two temperatures of water that you need. So it's something that just needs to be paid attention to in the design of these systems. Another thing that I mentioned earlier is the capacity limitations. So these radiant systems do have limitations on capacity. In an all air system, you can always just pump in more air. That's not the best idea, but it does increase capacity. With radiant systems, there are limitations. And so the building envelope becomes extremely important in making the use of these systems feasible. So looking at triple glazing, looking at increased insulation at the exterior, looking at both external shading and internal shading, whether that be motorized shading or electrochromic glazing. All of these things can help reduce the envelope load in the building and get the BTU per square foot requirement in the space down such that you can then apply these radiant systems. So, the envelope is very, very important in making these systems happen. Another item we touched on briefly was acoustics. So there's a benefit of these radiant systems in that they are extremely, extremely quiet, much more quiet than your traditional overhead all air systems. And the fact that they're very quiet can be sort of a blessing and a curse. In some instances, sound masking systems are actually required for, say, an open office application because people are used to a certain amount of background noise, a certain amount of HVAC noise. And when they don't have that, it becomes a little off-putting. So you'll see these sound masking systems incorporated as well. And finally, I wanted to touch on the architectural aesthetics. We've looked at a number of different implementations, and they all can look very, very different, right? So it's very important that engineers and architects work together and have an understanding of, what do you want the space to look like? How do you want it to feel? And then see if there's a radiant application that can sort of marry up with that architectural vision. So with that ends this presentation. I would like to plug our next presentation that will happen in 2 weeks. This one will be on stormwater reclaim and reuse. And the presentation will be by Kevin Cahill, who is one of the 2 principals in our Washington, D.C. office. So I hope that you can all join us again next time on July 8th between noon and 1 p.m. for that. And with that, I will open it up to questions. All right, let me open the little widget here. All right, so the first question is how to model and size radiant systems using energy modelers. Tip, strategies, references, software recommendations. So that's a great question. These systems can be extensively modeled just like any other. Basically, every commercially available modeling software has modules for radiant systems in it. So whether you're using Train Trace, Energy Plus, IES, all of these different systems can model both radiant floor slabs and radiant ceilings. So both high mass and low mass systems. There's a second question. can the thermal comfort be achieved irrespective of conditions inside the space? So from a thermal comfort standpoint, essentially every parameter, every one of those 6 parameters inside the space is going to come into play. So one can't really be achieved irrespective of another. There are things that you can do in terms of airflow velocities to try to maintain thermal comfort. One of which is, the idea of a ceiling fan. So you can have a much more higher elevated temperature, and if you have a ceiling fan, the fact that you have higher velocity air coming across your body actually makes you more comfortable. So there are ways to sort of change certain parameters to achieve that comfort, but it's very difficult to do it across a wide array, right? Some person might think that turning the ceiling fan on is making them more comfortable, while another might think that it's causing a draft. There's a question about what is the energy efficiency achieved? So when we're designing radiant systems, if I'm looking at a radiant system in a high performance building and I'm comparing that to an ASHRAE baseline, my target is typically going to be 30 to 50% better than an ASHRAE baseline. So these are significant improvements that you can achieve with these types of systems. And finally, I see, what is the heat recovery system used in the DOAS? So any type of energy recovery can be used in the DOAS system. In order to control humidity, oftentimes we'll see dual wheel systems. So we may see a total energy recovery wheel, which is pre-treating the outside air with the return air from the space. And we may have a second wheel, which could be a desiccant wheel, which we're kind of using to get free reheat, because in dehumidification mode, we're going to need to drive that temperature down, sometimes below 50 degrees, which is going to be too cold to deliver to the space. So we need to warm that air back up. So oftentimes the desiccant wheel might be used to do that. You can also use plate and frame air-to-air heat exchangers to get that sort of free reheat as well. So really any of the energy recovery options that would be traditionally available in a DOAS are still applicable to this. And so with that, it is 12:57, and I know that we all live in 1-hour increments now as we're all working from home. So I will wrap up the presentation now. Again, thank you all for joining. I really appreciate you spending the time today to learn a little bit about radiant systems. Thank you, and have a great day.
Thank you, Joe. That was fantastic. Thank you, everybody, for attending, and we do hope we see you all back 2 weeks from today at 12 o'clock to hear from Kevin about the sewer reclaim, or I should say the storm reclaim systems. Thank you so much. Have a great day.